repeated squaring technique. Yeah. So here I like to talk about two interesting techniques. Yeah. And also in our quiz questions, there are two questions related to these techniques, two questions. The first one and the last one. The first question number one and question number 10 in quiz 1 related to these techniques. Yeah. All right, so let me start the first technique. It's called the repeated squaring technique. So what's that? Yeah. So let me describe the problem first. Yeah. All right, the title, evaluate monomials based on square structure. All right. So what's the monomial? Okay, first, yeah. So it's we just finished studying polynomials, right? Yeah. But the monomial, it's a very simple form. Only one term, x to the nth. So that's the monomial. All right. Yeah. We can evaluate polynomial using the Horner's rule. Yeah. So why we need to look at a much simpler form, monomials. All right. Yeah. Here, something is interesting here. Yeah. All right. So here the monomial. Yeah. If we use the usual way to do evaluation, x multiplication between every two operands, yeah. Multiplication operands. Yeah. Okay, so if you count one, each dot corresponds to one multiplication, and you have total n operands of, yeah, n operands in between n minus 1 dots, right? So that corresponds to n minus 1 multiplications. Right? Yeah. The question is, can we do better than this? Can we do better than this n minus 1 multiplications? Right? Can you see a better way to find the value of this power form, power function, power form in a much faster way? That's interesting, right? That's interesting. Yeah. The answer is yes. There is a much faster way we can use to find the value of this power form. Yeah. All right. So how? Yeah. How to do that? Yeah. All right. So here, there is a smart idea. Smart idea. Okay. Yeah. So here, let me talk about the idea first. Idea. Yeah. Okay. Yeah. Idea. Let me start with some high level, the general principle that we use in our daily life. General principle. Okay. In our daily life, we want to do things efficiently, in a productive way. All right. Yeah. So when we want to do something, when we want to complete some tasks, we need to use resource, right? We need to use, a lot of resources. We know the resources. There is some cost associated with resources. It's usually resources not free and sometimes pretty expensive. All right. So you don't want to waste your resource. So you want to save your resources as much as you can, right? Yes. So in our daily life, in our mind, we tend to save the resources when we need to solve some problems, right? Now, here we take that approach, that kind of approach, okay? Yeah. So the idea is reuse the resources. Okay, yeah. So here, what I mean, the resources here, I mean something with useful values. So I treat as resources, okay? Something, useful, yeah. And not free, we need to pay, right? So not free, we need to pay on the resources. So we want to save the resources, right? Yeah. So here, now, let's look at the calculation part. Calculation, this power form, the general power form. We need to use resources, right? Yeah. So you need to pay necessary costs to do the calculation here. All right, yeah, here. When we do that, we try to reuse the resources we need. We pay to get the resources. We need to reuse the resources we already paid. That idea, okay? All right, so let me show you a simple example here. All right, now, in this example, we want to calculate x to the fourth, this power form, this monomial power form, x to the fourth. All right, yeah, okay. If we use the old way, yeah, old way, x dot, four x's, 4 copies of x, right, with 3 dots, then it gives us 3 multiplications. All right, so now new way, okay, yeah. So new way, we try to use this idea, reusing the resource idea here. Okay. All right, yeah. X to the fourth, this time, x dot x, 1 multiplication. 1 multiplication gives us x squared term, right? X squared term. We have the value. Okay, we already have this value after calculation, after first round calculation, right? Yeah. Okay, we have it. Or this item, after we get a square, we already paid, right? It's not free, right? when you do calculation, x times x, you need to pay something, right? Yeah. Although you may feel it's very cheap, yeah, but you need to pay something here, all right? So it is paid. So we have that value in our hand. So the question, do you want to pay it again? If you already have the value, the next time when you need it, do you need to pay it again? No, you don't need to pay. You have it. You just reuse it, okay? It is already in your hand. You just use it directly. Don't pay it another time, right? Okay, so now the next time, because x to the fourth, so we have another x squared, but the second time we don't pay. So we do not pay here because we reuse it. We use our existing version copy, right? We use something we have paid, okay? Do not repay it. All right, now, based on this understanding, let us count how many multiplications do we need, right? Yeah. Multiplication one, the first time we pay it, all right, pay for it, one multiplication. Then second time here, we have to pay two multiplication, but we do not pay this copy for this copy, all right? Yeah, that copy we can save. We do not pay, all right? Yeah. So now, as a conclusion, you can see we do the reduction. We only need two multiplication. Yeah. All right, we improve it. So think about that. So here, the reason here we can save a few more multiplications, you can see, because we explore the square structure. We take advantage of the square structure, okay? In other words, if we can find squares, then we can save some multiplications. So that's the conclusion from this example. Okay, yeah. All right, so, a question. Are the X in the old way being paid? Oh, yeah, all right, yeah, good, yeah. So your question, are the X in the old way being paid for every, or because here, what do we say pay? We mean when we do multiplication, we pay something. Think about that. When we do multiplication, all right. So the old way, the copy, each copy, we do not do multiplication, right? Each copy, we grab it, we put there. So here, let's talk about, one multiplication corresponds to the, the basic cost we need to pay, right? Pay for what? Yeah. What, let's say this way, each multiplication is not free. We need to use computing resource to do multiplication. That's what we mean, we pay. But all the way, each X, if you only look at each X, there is no multiplication involved. That means we do not pay anything, right? Yeah. So that's why we do not say we pay. Okay. Yeah. All right. Yeah. So we just put there. Yeah. All right. Now, next. So this idea, let us generalize to the form. So here now think about, we can consider still power form with n power of 2. How about that? Power of 2, that means n equals 2 to the kth power. Okay? Yep. Because in that case, we can take advantage of that square structure again, and again for k times. How about that? K times. How about that? Okay? Yes. All right, so now x squared the first time, 1 multiplication. All right. X to the 4th equals x squared times x squared, right? So you can see 2 multiplications, all right? Yeah. X to the 8th, look at that. X to the 4th times x to the 4th, all right? X to the 4th, the first one, we pay two multiplications. That's the cost we pay, all right? Then we just add 1 for the dot in the middle, but the second copy x to the 4th, we reuse. Second copy, we can reuse, all right? So then we only need to add 1 more multiplication. That's 3. Yeah. Similarly, x to the 16th, x to the 8th times x to the 8th. The first copy of x to the 8th, we pay 3 multiplications. The second copy reuse. Then the dot in the middle, we have to pay that cost, right? So the answer 4 multiplications. All right? Yeah, that's enough. We can go until we reach x to the power of 2 to the kth. Yeah, 2 to the kth power. X to the 2 to the k minus 1. First copy, dot, x to the 2 to the another 2 to the k minus 1 copy. The first one we pay k plus 1. Yeah, just the same number as the exponent. All right. Then add 1 in the middle dot and reuse. So the answer k multiplications. How about that? So you can see we can save a lot. We can save a lot. Yeah. So here, let's consider this question. How much? How much do we save? Here, okay? Yeah. Let me use a simple example to show how much do we save. Okay, yeah. Here I take a special n, power of 2, n equals 1024. You're familiar with this number, power of 2, right? 2 to the 10th. So it is a famous power of 2. 2 to the 10th. All right. Then now comparison all the way. Okay, all the way. Without reusing the resource, that all the way. Okay, without using resource all the way. We need 1023, the degree number minus 1, 1023 multiplications. Okay, yeah. Now a new way, reusing resource. Okay, yeah, new way. In other words, without doing redundant calculation. No. New way, k equals 10, right? In this particular example, this k corresponds to 10. That means 10 multiplication. How much you saved? From 1023 to 10. Is that big save? Look at that. Is that big saving here? Right? Yeah. Even you do not look at that 1023, more than double that 10, right? Look at that. But there is a big 1000. Look at that. That saving is huge, right? Yeah. Look at that. Okay. Yeah. All right. Yeah. This example, you can see our new method. Yeah. We call it repeated squaring. The name repeated squaring. Yeah. The new method. Much better, right? Yeah. Okay. Then now you can answer question 1 of quiz 1 better, right? Question 1 of quiz 1. The higher the degree, the smaller the number of multiplications, right? Here, the higher the degree, look at that. The higher the degree, 1000 something, pretty high, right? The number of multiplication using this new technique, only 10. Only 10. Look at this example, okay? So when you try to answer question number 1, use this example there, all right? So here the degree more than 1000, greater than 1000. But think about, you have a polynomial a0 plus a100 x to the 100. That degree only 100. This 1000 is much higher than the 100, right? But this polynomial, you need 100 multiplication, right? But here you only need a 10. Can you compare? Consider this example here, right? Yeah. All right. Yeah. Here, implementation recursively, we can implement this idea, using a recursive function call. Yeah, but here I do not have space. Yeah. So I need to later I talk about this idea. Okay. Yeah. Recursion idea for implementation.